this video here provides you with a worked out example for determining the price of assets using the risk-neutral Q pricing measure. Now I've chosen an example from the fixed income market. The example guides you through the Vasicek model for the term structure of default-free bonds. In a strict sense, that is a model for inflation-indexed default-free bonds, or in short, real bonds. Moreover, in addition to the math, I also add economic thinking, which arises from equilibrium asset pricing model, such as Merton's in a temporal CAPM, or the general class of consumption-based asset pricing models, to give you intuition on the sign of the bond risk premium and to tell you how it relates to hedging non-diversifiable risks. Now the overall length of the video will be longer, hopefully not much longer, but I'm afraid it will, than the other videos. But I didn't want to slice the derivation into sub-videos. So therefore, if you want to understand how to derive the Vasicek bond pricing model plus some economic insights, go for the video. Otherwise, enjoy the afternoon. So let's start with the setup, followed by a solution plan. The solution strategy will consist of 4 steps. This video takes the necessary time to talk about each of the 4 solution steps in the required detail. So we assume the short rate RT follows a linear Ito-stochastic differential equation, both under the empirical distribution P and under the risk-neutral probability measure Q. So mathematically, that's the dynamic of the short rate under both probability measures. So note dz are Gaussian interest rate shocks. Also note the terms R bar and kappa have the interpretation of the long-run mean of the short rate and the speed of mean reversion, respectively. So in my slightly simplified version of the Vasicek model, I assume that only the long-run mean can be different under the P and the Q probability measure. That assumption is equivalent to the assumption that the ex ante expected risk premium for interest rate shocks is a constant, which I denote as lambda r. Now, by Gaussian theorem, it holds that dzq can be rewritten as dzp plus lambda r dt. So plugging the last identity into the first equation reveals the equilibrium relationship between the long-run mean of the short rate under P and under Q. Mathematically, that means the following. So let's look at the second expression on the right. It tells you that the priced-in long-run mean differs from the long-run mean in data if the ex-ante expected risk premium is non-zero. Depending on the sign of the risk premium, the priced-in long-run mean can be higher or lower than the data counterpart. If lambda r is positive, the priced-in long-run mean is below the data counterpart. That implies that the price of long-term bonds appears to be relatively expensive compared to the long-run mean of the time series of RT. But that would be an equilibrium and hence a no arbitrage outcome. In fact, based on economic reasoning, for example, by using Merton's intertemporal CAPM, we can denote that a relatively high equilibrium price for long-term bonds goes along with a representative investor who considers these long-term bonds to be a good hedge instrument against systematic risk. But which systematic risk could that be? According to the intertemporal CAPM, that is either a hedge against market risk or a hedge against a reduction in the level of the capital allocation line or a hedge against a flattening of the capital allocation line. The most straightforward reason is the second one, is the hedge against the reduction in the level of the capital allocation line. That is because a surprise reduction in RT lowers the level of the capital allocation line, which coincides with a worsening of current investment opportunities. At the same time, a surprise reduction in the short rate makes the bond pay out more than expected. Especially long-term bonds pay out more than expected because of their long duration. Hence, a long-term bond is a hedge against the worsening of current investment opportunities. And the risk-averse investor likes to hold such an asset in his portfolio, even if it appears relatively expensive. Now let's get back to the valuation problem of the term structure of bonds. Vasicek in 1977 derived the price of a default-free bond with maturity tau. So the price of that bond is denoted as BT of tau, and it's defined to be the risk-neutral conditional expectation of $1 you receive in T plus tau discounted by the risk-free rate. And Vasicek solved that conditional expectation in closed form and showed it coincides with e to the minus aq of tau minus bq tau times RT, where aq tau and bq tau are deterministic functions of the short rate parameters under Q. I will now show you how to solve the following problem. We use 4 steps to do so, and the steps are as follows. First, we apply the integrating factor approach to get the distribution of RT conditional on F0. Second, we determine the integrated short rate. Third, we take the exponent of the integrated short rate. And fourth, we take the expectation of that last expression. So let's go through all the steps in detail. So step 1. We now apply the integrating factor trick to the linear SDE. If that is not clear to you, I advise you consult my video on solving linear SDEs with the help of the integrating factor. Otherwise, I invite you to verify that RT conditional on F0 follows the following Gaussian distribution. As an additional example, you could also verify that the expectation of RT under Q coincides with the following expression, while the variance of RT under Q coincides with that expression here. And for fun, why don't you also verify that the limit of the expectation of the short rate under Q for t going to infinity equals the following expression. while the limit of the variance equals with that ratio here. Okay, now step 1 would be complete. We have found that the conditional distribution of the short rate is Gaussian, with first and second moments as stated above. Now we move on to step number 2. The goal is to characterize that integral, which I denote as I indexed capital T, which is simply the integrated short rate. Now, I argue that is doable, because RT conditional on F0 is Gaussian, as we know from step number 1. Hence now we have to add up Gaussian random variables. And the solution will be Gaussian as well. So the only potential obstacle on the way is the application of Fubini's theorem, which will allow us to change the order of integration. Now let's look at that in detail. Let's just plug in the solution of RT from step 1 into the integration operator. We hence write I capital T as follows. Now let's inspect the last integral. Now, the first 3 integrals, they are plain Riemann-like deterministic integrals. Therefore, they won't pose a challenge. It's that last integral, that last term, which is potentially troublesome. Now, that term consists of a double integral. That itself is just like a double sum, so in itself not a problem. The only thing is more a matter of convenience. We are asked to first get the stochastic integral and then second to integrate that stochastic solution across time. It would be more convenient to change the order of integration, meaning first integrate across time and then treat the stochastic integral as a Gaussian random variable. Now technically that is doable. Fubini proved once a lemma that says that you can change the order of integration, yet you need to make sure that the integration boundaries are adjusted accordingly, so that in the end you really integrate over the exact same area. Now the best way to ensure that is to draw a picture where you explicitly check for the integration upper and lower bounds. Okay, now let's continue with the integrated short rate. I invite you to verify that you can rewrite the integrated short rate as follows. As you look at the last term, you see how I have adjusted the integration boundary when swapping the order of integration. Now pause here for a while, or at least flag that integral to make sure you understand the Fubini trick. Otherwise, you might not be able to generalize that example to more complicated pricing models. Now I continue with the double integral. Note that the double integral can be rewritten as follows. Now, we cannot simplify the Gaussian integral any further. The only thing we can do is to express that as a Gaussian random variable with known first and second moments. Doing so allows us to express the integrated short rate as a Gaussian random variable. And again, I invite you here to show yourself that the integrated short rate follows the following Gaussian distribution. Okay, assuming you have invested some time to verify the above solution, we can now proceed to solution step number 3. We need to get the exponential of minus the integrated short rate. Now, as we have the solution for the integrated short rate, minus the integrated short rate in the exponential will be rather straightforward. So there isn't much to do. That solution step number 3 gets a check right away. We hence move forward towards solution step number 4. We now need to take the conditional expectation of the last expression. And that again is a manageable task. The expectation of an exponential that has Gaussian random variables in that exponential coincides with the exponential of the expectation plus half the variance. Hence the solution is as follows. So we have now found the equilibrium price, we can also say the no arbitrage price of the term structure of default-free bonds. Now, if you wanted to express the bond price as a continuously compounded yield, you could simply state the yield as follows. Now, as you plug in the parametric expression for the bond price, you get for the yield the following expression. And now you could take that last expression to ask yourself where long-term yield converge to. Now, if you do so, it reveals that y infinity, which is my expression here for the limit of the yield if maturity goes to infinity, now that limit coincides with r upper bar q minus sigma square r divided by 2 kappa square. Now that expression coincides with the priced in long run mean of the short rate minus a Jensen term that captures the convexity of the natural logarithmic function. If you want to better see how the ex ante expected risk premium affects the long end of the yield curve, you can re-express the last equation under the empirical probability measure P, and you would arrive at the following expression. Therefore, if you wanted now to see explicitly that the equilibrium expected return on the bond is below the risk-free rate, you would have to do the following. First, you regroup constants and short rate components in the bond price to write it as an exponential affine function in R. I invite you to verify yourself that the bond price can be rewritten as follows. Now, second, the instantaneous return from holding that bond is simply dB over B equal RT dt minus BQ tau times sigma R times dz RTQ, which I have written down here under the risk-neutral probability measure. That itself confirms that the conditional expected return under Q is simply the short rate RT. Now you have to write the bond dynamic or the bond return under the empirical probability measure P if you wanted to see which risk premium you're expected to earn. So, relying on Gaussian's theorem, we rewrite the last expression as follows. The bond return equals RT minus BQ tau sigma R lambda dt minus BQ tau sigma R dZRT P. That last expression supports the intertemporal cap M intuition for the bond premium that I shared with you at the beginning of this video. Now let's go through that again. Look at the parametric expression for BQ tau. It is positive for all maturities tau larger than 0. When you look at the bond return expressed as the E to SDE, you see that a negative interest rate shock in the data makes the bond return earn more than expected. We can write that as dBT over BT, realized bond return, is larger than its conditional expectation for dZRTP smaller than 0. Intuition-wise, that is the result of the inverse price-yield relation. A lower yield or a lower interest rate goes along with higher prices. So going back to the ICAPM, you note that as a price worsening of the current investment opportunity set, meaning a lower short rate than expected, coincides with a higher bond return than expected. Ergo, the bond in the Vasicek model hedges the risk of a lower than expected capital allocation line. And that hedge capability makes its expected return to be below the risk-free rate. So I restate that in math terms. The conditional expectation of the bond return under the empirical measure P is below the risk-free rate because lambda R is positive. So again, if you ask yourself, why again was lambda R positive? Well, that is due to the equilibrium considerations of the intertemporal cap M that I've just mentioned. Now last for this video. Consumption-based equilibrium asset pricing models give you the same answer, just from a different angle. These models would imply that periods of lower than expected consumption growth are periods where the real short rate is lower than expected. Hence, the price of a real bond is above expectations. And that implies that real bonds hedge consumption risk, and hence they trade in equilibrium at a premium. And this premium makes real bonds earn a negative risk premium.